Okay, so in the last video we saw how to construct an algorithm for factoring integers on a quantum computer. So we saw the actual quantum circuit that carries it out, except that that quantum circuit involved the quantum Fourier transform. And we haven't yet seen how to carry out the quantum Fourier transform efficiently using a quantum circuit. So in this video I'll show you how that can be done, implemented efficiently. So in order to do this, we have to understand some of the structure of the Fourier transform. And this is a beautiful structure that actually goes into the construction of a fast Fourier transform circuit in the classical case. So let's do a review of that first. So first, remember what the Fourier transform matrix looks like. It looks like the entries. It's an n by n matrix whose entries are the primitive nth roots of unity. So omega is a complex number such that omega to the n is equal to 1. And in fact, there are n such roots. So omega is the primitive nth root of unity. So omega is e to the 2 pi I over n, which is cosine of 2 pi by n plus I sine of 2 pi by n. Okay, it's this complex number. And now, how does the okay, so in the classical case, we don't actually normalize our Fourier transform matrix, so we don't multiply by 1 over square root n, so it's not actually unitary. Okay, and it takes as input an n-dimensional vector, a complex vector, and it outputs an n-dimensional complex vector. So b0, b1, bn minus 1. Okay, so that's our n-dimensional Fourier transform, a discrete Fourier transform. And now we want to understand how to implement this efficiently. So first, let's see how to implement it efficiently using a classical circuit. Okay, so remember, usually if you multiply a matrix, n by n matrix, by an n-dimensional vector, it requires n squared operations, because for each entry of the output, we must take the corresponding row and multiply it by this column, and that takes n operations, and so it's n per entry, so n squared total. So in the fast Fourier transform, we do it much more efficiently in order n log n operations. And this relies on the structure of the Fourier transform matrix. So what's the structure of the Fourier transform matrix? So what we, remember what we said, the jkth entry of the Fourier transform matrix is omega to the jk. Now what we're going to do is we're going to sort the inputs in this clever manner. So we sort them into the even numbered ones and the odd numbered ones. So that corresponds to sorting the columns, where we put the even columns here and the odd columns there. So now the entry in this particular entry is going to be omega to the 2j times k, and this entry is omega to the 2jk times omega to the j. Now let's go ahead and sort the, let's divide the columns into two. So the columns, the first half is the columns with index less than n over 2, and the second half is greater than n over 2. So we have row j versus j plus n over 2. And now notice that this entry, of course, was omega to the 2jk, but this is also omega to the 2jk, right? Because what we have is this entry is omega to the j plus n over 2 times 2k, which is omega to the 2jk plus n times k. But remember, omega to the n is 1, so omega to the nk is just 1. So we can drop that. That's what this is. And similarly, you can check that this entry is omega to the j times omega to the 2jk, and this entry is minus omega to the j times omega to the 2j. Now here's one more important thing to realize. So remember, omega was a primitive nth root of unity. It was e to the 2 pi I over n. Now what's omega squared? So omega squared is an n over 2th root of unity. In fact, it's the primitive n over 2th root of unity. It's e to the 2 pi I divided by n over 2. Right? So if you look at this matrix, it's an n over 2 by n over 2 matrix whose jkth entry is omega squared to the jk. Okay? So this is really, if we call this large matrix F sub n, then this matrix is F sub n over 2. So it's this matrix, it's F sub n over 2. How about this one? Well, it's almost F sub n over 2, except that the jth row of this matrix is multiplied by omega to the j. So let's write it like this, even though that's notation we've just invented. How about this matrix? It's also F sub n over 2, except that the jth row is now multiplied by minus omega to the j. Okay. This should make it a little reminiscent of the Hadamard matrix, where you have the Hadamard matrix was h sub n over 2, h sub n over 2, h sub n over 2, and minus h sub n over 2. So now it's slightly more complicated, but it's still very reminiscent of the Hadamard matrix. And so it's this structure that allows us to give this efficient circuit for computing this this transformation. So now let's see what, if we sort our inputs in this way, evens first, odds later, then how do we actually do this multiplication? So, well, what we can do is move this inside, and so it's as though what we would be doing is we'd be taking this top half and multiplying it here, and this top half and multiplying it here, bottom half multiplying this with it, and bottom half multiplying that. So let's just write it out carefully. So we basically have our Fourier transforms of n over 2. Sorry, we changed notations in the middle. By this m, I mean just f sub n over 2, f sub n over 2, and now we are taking the evens here, odds here, and of course we must multiply the jth row by omega to the j and minus omega to the j. Okay, so now this should tell you how to construct a circuit for this problem, and how to make the circuit. It's going to be a recursive circuit. So what we'll do is these are our input bits. So we sort them, we take the even ones on top, odd ones on the bottom, and now these we put through a Fourier transform matrix. We do a Fourier transform of these. It's an n over 2 by n over 2 Fourier transform. We do a Fourier transform of these, and then what do we need to do about them? So remember, what we need to do is, on top we need to take this plus this, except in the jth row we have to multiply this answer by omega to the j. In the bottom we need to take this minus this, except in the jth row we multiply this by omega to the j. And so if you think about it, what that means is you put this through the Fourier transform matrix, and now on the jth output you take this, the jth output from the bottom, multiplied by omega to the j, and you add these two values, right? On the bottom, what you do is, here, let's take this out. What we do is you multiply the bottom value by omega to the j, you take this value and you subtract this from that, and that's your output. Okay, so that's our circuit for the fast Fourier transform. And now you can see that the size of the circuit for size n is 2 times the size for n over 2, and plus you get order n gates, and this gives you that the total size is order n log n. Right? This is the fast Fourier transform circuit. It's of size n log n instead of n squared, which is what you'd expect naively. So now let's apply this in the quantum setting. Okay, so in the quantum setting, let's go back and reinterpret everything. So now I'm going to switch from n to capital M. Okay, why are we doing capital M? So we'll think of, okay, so we'll think of capital M as being 2 to the little m. And the reason we do that is because our inputs, these are the amplitudes for our, so we think of having little m qubits, and so their quantum state is described by a 2 to the little m dimensional complex vector. So that's a capital M dimensional complex vector. So those amplitudes are alpha naught through alpha capital M minus 1. And now what we want to do is we want to perform a certain unitary transformation. So to make this transformation unitary, we have the usual Fourier transform matrix that we did classically, except now we must normalize it by 1 over square root of n. So now this becomes unitary, it preserves length. And so in order to carry out this transformation, what we do is we take these little m qubits and we feed them into a quantum Fourier transform sub m circuit, and what we get out is little m qubits whose state now is described by this. It's beta naught through beta m minus 1, which is exactly this Fourier transform applied to the input vector. Okay, so now we want to understand how to carry out this transformation using an efficient circuit. Okay.